Okay, let's jump right into this explainer. Have you ever really thought about the sheer physical reality of how machines actually process human imagination? I mean, every time we type a prompt, we're treated to this magic show of fluid ideas, stunning art, and complex reasoning on our screens. But right beneath that smooth, glassy surface, well, there is a strict, completely unforgiving mechanical reality that governs literally everything we do in the digital age.
And so, we start our journey today with a genuinely profound mystery. How exactly do we cross the bridge from the boundless associative realm of our ideas into the rigid, microscopic, and highly literal world of silicon execution? How does a fuzzy thought, a poem, a business strategy, just a simple command, actually trigger the physical logic gates inside a computer chip?
Section 1. The Human Operating System.
To really understand this transformation, we've got to start at the wide end of the funnel, our own minds. Take a look at this model by C.S. Peirce. It shows cognition as this incredibly dynamic loop. We are constantly, naturally taking our fuzzy mental symbols and actively mapping them down onto physical material substrates. We humans have literally always done this, right? Whether it's carving symbols into clay tablets thousands of years ago or tapping out Morse code on a telegraph. We instinctively extract features from our thoughts and force them into physical patterns.
So in other words, our minds act as what researchers are calling OS alpha. That's right, your own brain is essentially the primary operating system. This deeply human drive to take abstract thoughts and structure them into physical tokens is actually the foundational blueprint for absolutely everything a modern computer does.
Section 2. AI Continuous Vector Spaces. Now, this perfectly captures the dramatic tension of modern computing. We're trying to take these beautiful, continuous AI vector spaces, spaces that are fuzzy, highly associative, infinitely dimensional, and somehow cram them into harsh, discrete token boxes. It's kind of like trying to pack a literal cloud into rigid cardboard moving boxes. The hardware itself simply cannot process fluid meaning. It can only deal with exact, rigid numbers.
Deep inside the AI, concepts live in this boundless, continuous space. Meaning here is entirely probabilistic. It's highly dimensional. It's almost like a watercolor painting of human intuition. The AI can literally do semantic arithmetic. For example, it can take a mathematical vector for Jennifer Aniston, shift it toward Friends by adding the vector for TV series. It is a completely fluid geometry of meaning.
Which brings us to Section 3, the 7-bit ASCII bottleneck.
So here is the crucial catch. To actually do anything real in the physical world, all of that beautiful fluid math hits a brutal, narrow constriction point. Before an AI can execute an instruction, it absolutely must pass through the mandatory translation layer of tokenization. Look, AI doesn't see language, it sees discrete numerical IDs. And because it relies on historical constraints like legacy 7-bit ASCII and UTF formats, algorithms like byte pair encoding have to arbitrarily chop up our words, and they do this based simply on how often characters appear together in training data, not based on what the words actually mean. This creates a massive modality gap between fluid thought and rigid computation.
And you can see here just how badly this rigid bottleneck shatters meaning. Because tokenization is character-based, something as simple as capitalizing a letter changes everything. The words good with a lowercase g and good with a capital G become entirely different token IDs. The AI literally has to waste compute power just to learn they mean the exact same thing. Adding a space before a word alters its boundary completely. And trying to process the number pi? Oh, it's a total disaster. 3.14159 fractures into totally arbitrary chunks like 3.14 and 159. Because these discrete boundaries don't align with actual decimal math, the AI can't systematically do arithmetic. It's basically just memorizing text chunks.
Let's move to Section 4, the Silicon Rosetta Stone.
Now, despite those massive mathematical vulnerabilities we just talked about, this bottleneck is absolutely necessary. Text, and specifically highly structured text like JSON or Python, acts as our Silicon Rosetta Stone. It is the ultimate semiotic bridge. Think of it as a sort of divine script that takes the AI's fuzzy, probabilistic hallucinations, completely strips away the ambiguity, and tames them into a strict, verifiable format. Without this 7-bit ASCII interface, the continuous dreams of the neural network could never, ever connect with the rigid logic gates of a physical processor.
Next up, Section 5, Reaching the Physical ALU. Let's walk through how this all builds to the ultimate climax,
We start with that fuzzy, probabilistic intent from the AI. We squeeze it forcefully through the ASCII tokenization bottleneck we just discussed. But then, instead of just letting the AI guess the answer, modern systems compile that intent into static, validated code. And finally, that code triggers purely deterministic actions in the physical arithmetic logic unit, the actual microscopic hardware doing the math inside the processor.
By forcing AI through this exact compiling pipeline, we are explicitly trading runtime flexibility for 100% determinism. And guys, this is huge. In normal runtime inference, you might see anywhere from 18 to 75% output variance. That means the AI might give you a slightly different answer every single time you ask. But compiled AI, it eliminates that output variance entirely. It achieves full auditability, which is absolutely essential if you're dealing with things like FDA compliance in healthcare or strict automated enterprise workflows. Plus, generating the code just once and running it statically saves up to 57 times the computing tokens.
Advanced architectures are taking this even further to solve those exact tokenization math failures we looked at earlier. They use state handoff mechanisms, like the yield protocol, to literally pause the AI's probabilistic dreaming. Think of it like stopping a creative brainstorm just to use a calculator. When the system hits a math problem, it completely stops the neural network, hands the state over to deterministic transformer circuits to execute a precise physical calculation right at the transistor level, and then hands the exact answer back to the language model.
This brings us to a really profound realization about this entire architecture, perfectly captured here by this quote regarding Alan Turing and John von Neumann. It honestly blew my mind to realize that text isn't just symbols anymore. It is physical action. We have successfully merged signs that stand for cognitive meanings with signs that trigger physical operations. Through the semiotic bridge, the words we type literally command the physical universe of silicon.
So I want to leave you with this final thought to ponder today. We've built an incredibly powerful system that translates our boundless human operating system straight down into the microscopic certainty of physical hardware. But if all human imagination absolutely must be squeezed through this rigid, lossy, 7-bit ASCII bottleneck just to become physical reality, what subtle nuances, what continuous beauties of human thought are getting lost in translation? Thanks for exploring the semiotic bridge with me today. Keep questioning the structures beneath the screen.